Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Nasrullah bin Abdul Razak. So today we will be presenting about our group assignment of industry visit in the Spirit Aerosystem.
These are our team members.
I will presenting the purpose of visit to the Spirit Aerosystem. There are three primary objectives of our visit. First of all, we have uh, to observe real industrial engineering practices in aerospace manufacturing. So, when we go there, we can observe real time aerospace manufacturing that we can saw it in our class. Next, to conduct a time study on actual production processes. So when we go there, we can observe the technician doing the task. Then we can measure the duration, and we able to determine the standard time on the industry. Lastly, to compare theoretical time study method with industry practices. So we can actual saw the process, then we can compare it from the real time and the theoretical that we learn in our class. This will help us to understand how industry optimize their efficiency without sacrificing their safety or quality. uh, Company background of the Spirit Aerosystem. So, what is a Spirit Aerosystem does? Spirit Aerosystem is a global aerospace manufacturer of aerostructure. They produce fuselage section, wing component, and structural aircraft part to the major aircraft manufacturer in the world, such as Boeing and the Airbus. But not just that, they also support commercial and defense aviation program. Everything they do is about high precision and manufacturing to make sure every part is perfect.
Problem statement. In our study, we identified a key challenge in time study methodology. The formula we learned in class different from the one applied in industry. The theoretical formula calculates standard time by dividing normal time with 1 minus the allowance. Meanwhile, the industrial formula multiplies normal time by 1 plus the allowance. This difference may seem small, but it has a big impact. It changes how productivity is measured, how resources are planned, and how realistic work standards are set. So, the problem we are addressing is the gap between classroom theory and actual industry practice, and understanding why this difference exists. To tackle this problem, our project has several objectives. First, we wanted to understand industry practice in time study by observing real aerospace manufacturing tasks. Second, we aim to collect and analyze real-time data recording observed time over 5 cycles using stopwatch measurement. Third, we compare the theoretical and industrial formula to see how each affects standard time calculation. And finally, we apply industrial engineering tool to propose improvement in efficiency and ergonomy. In terms of scope, our study was based on industrial visit to Spirit Aerosystem Malaysia, focusing specifically on two tasks, the drilling process and the countersunk process.
So, I will continue for the next two parts, which is methodology and process flow. So, for the introduction of methodology, the visit was carried out at Spirit Aerosystem Malaysia, and we are assigned to the radio manufacturing area. This is to perform a time study and analysis for the manufacturing process. So, our team has been assigned to collect data for two different tasks, which is the drilling task and the countersunk CSK task. So how we carry out the time study and analysis? First of all, we observe the procedure step by step for each task. Next, the data are recorded over 5 cycles to calculate and observe for any differences. We use the observation sheet that from Spirit and the stopwatch to record the time study. The observation sheet was prepared from Spirit. Then we continue to record the time for each task in minute and second for each activity. For the next part is process flow. So for the drilling task, there are many procedures to follow to complete the task, which is firstly connecting the air hose to the compressor. Next, attaching the air hose to the drill gun. After that, the workers need to install the drill bit, stopper and the drill guide. After that, he will performing the drilling operation on the test piece. After that, he need to changing the drill bit with the deburring set. Then performing the deburring process. Lastly, inspecting the hole using go or no go gauge. That's for the drilling task. So for the countersunk task, CSK task, the procedure is much less, but the time is still consuming because there are some adjustment or setting that required to be performed. So first of all, the first part is attaching the air hose to the drill gun, same as the drilling task. Next, installing the countersunk tool. Then performing the required setting and adjustment. After that, carry out the countersinking operation. Lastly, conducting the fastener test.
Next, we will move to the result and analysis. Firstly, we conducted a stopwatch time study for 2 processes, where each process was observed over 5 cycles. Each task was broken down into smaller elements so that we could analyze the time contribution more accurately. For process 1, the total cycle time ranged from 84.7 seconds to 122.1 seconds, with an average cycle time of 107.54 seconds. From the element level analysis, the element 3 was identified as the most time-consuming element, contributing about 44% of the total cycle time. This element also showed the highest variation across cycle. For process 2, the cycle time ranged from 69.1 seconds to 92.7 seconds with an average cycle time of 77.36 seconds, which is element 4 is recorded the highest average time, while element 3, 5 and 7 show noticeable variation. Overall, we observe that only a few elements dominate the total cycle time. The variations seem normal in real industry environments and are mainly caused by operator movement, tool handling, and minor adjustment during the test. Okay, now for standard time comparison. First, a performance rating of 1.1 was applied to adjust the observed time to normal time. This assumes the operator was working slightly faster than the standard pace. Next, a 50% allowance was added to account for personnel needs, fatigue, and unavoidable delays. We then compared two methods of standard time calculation using the theoretical formula. The standard time obtained was 159.16 seconds for process 1 and 91.1 seconds for process 2. Using the industrial formula by Spirit Aero System, the standard time was slightly lower at 136.03 seconds for process 1 and 88.96 seconds for process 2. Although the difference are small, around 3 seconds for process 1 And 2 seconds for process 2. This difference can become significant when applied over multiple cycles, operator, or shifts. In conclusion, the theoretical method is more conservative, while the industrial method is more practical for real-time production planning.
Based on our observation, we identify several improvements that could reduce the overall cycle time. First, for the drilling tasks, many setup activities were repeated multiple times. These steps can be standardized and completed once at the start of the shift to save time. Second, instead of changing drill bits for debris, workers can use two separate drill guns, one for drilling and one for debris. This eliminates unnecessary tool change time. Next, for the countersunk task, the adjustment of the CSK tool took a significant amount of time. By standardizing the setting for similar materials or tasks, this time can be reduced. Finally, improving the layout and placing tools closer to the operator can minimize movement and help make the workflow more efficient. In conclusion, this industrial visit allows us to understand how time study is applied in real aerospace manufacturing. We observe that cycle times vary due to operator movement, tool handling, and setup repetition. From our analysis, element 3 in the drilling task and element 4 in the countersunk task contribute the most to total cycle time. We also compared the theoretical and industrial formulas for standard time. The industrial formula produce slightly lower values, which is more suitable for practical production planning. Overall, our proposed improvements can reduce unnecessary delays, improve workflow consistency, and support higher productivity in the manufacturing process. Thank you for viewing our presentation. On behalf of all five members, we appreciate the opportunity to present our analysis and findings. Thank you.